Hello, I'm Parth Reddy and I'm going to talk about how I solved the technical challenge at work. I am involved in exploring the subsurface of the Earth using geophysical measurements. Sound waves are sent into the Earth using a seismic source. They reflect back from horizons underneath and are recorded on the surface with geophones. Each geophone record is a time series. My job is to make sense of billions of such recordings and produce an image of the Earth like this. We are going to talk about how I remove the effect of the near-surface geology from the data. Here is an ideal scenario. Geophones are placed on a flat surface. The seismic energy recorded from a reflector deep beneath the surface shows the real geology. In the real world, however, the Earth's surface is highly undulating and the velocity underneath is variable. So the reflector image is distorted. To remove this distortion, a series of time shifts are applied to billions of geophone recordings. This time shift is the thickness of the near surface layer divided by the average velocity of the layer. So the problem was to calculate time shifts by analyzing over 56 billion data points and solve for hidden information not seen by body waves but seen by surface waves, and obviously do it as efficiently as possible. The conventional approach analyzes only body waves and uses all the geophone recordings, that is 56 billion recordings, hence is technically inferior and expensive to implement. This is a simplified graphic of the near surface. We see the highly variable weathering layer on the top characterized by low velocities. These are the sand dunes. Instead of analyzing their velocities from seismic recordings, I used a statistically calculated relationship of average velocity versus sand dune thickness to compensate for them. By compensating for the sand dunes, I was able to move the geophones to a smoother surface and geology, effectively taking out all the high frequency variations in time shifts. Since the residual near surface to be compensated is much smoother, I was now able to drop data points by 1 by 50, reducing the effort of analysis, both human and compute time, for body wave analysis. The geophones also record the surface waves. To use this information, the fundamental mode had to be correctly interpreted. So I had to come up with a workflow which can automatically interpret the fundamental mode of surface waves. I used a combination of noise rejection, data-dependent regression, wavelet shaping techniques to build this automatic workflow. My workflow reduced the turnaround time for this step from 15 days to 2 hours and is used as best practice all over the world. Finally, with the body wave dataset and surface wave dataset, I was able to integrate them with the joint inversion workflow to produce a consistent near-surface velocity model that integrates information specific to both of the measurements. To know more about this method, you can have a look at this paper which I have presented in the biggest annual Geoscience International Conference in Madrid 2015. So I solved the issue by simplifying the problem with data redundancy techniques and by approximating the high frequency part of the solution, integrating different measurements, and by automating the most time consuming step of the solution. All of this resulted in savings on production time and manpower usage, increased business for Schlumberger, and global best practices and methods. Thank you.